Oh, isiqalile. Greetings to you all. My name is Umzamo Wakashabalala. So basically, I'm doing this video to do some nice concepts on the portfolio theory part. This is a topic from financial mathematics. I even heard people saying that it is also studied in economics, but I'm not an economics major, so I don't know anything about what these guys are doing there. So we are going to do small things that are related to this portfolio theory part. Basically, my focus on this video will be on the mean variance analysis. So right now, currently, we are still studying the capital asset pricing model. So I'm planning to do that when we are done in my lectures, like in my class, when we are done studying that capital asset pricing model. And then I'm planning to do a video if I understand that very well. But let's continue on the Markowitz mean variance analysis. So we're done with this part in my class, so that's why I'm able to do this video, because I really enjoyed this part from the class. Basically, what is the whole idea behind these portfolio theory parts? Okay, it's like you go and invest your money. When you invest your money, you want to get profit. You want to make returns. That's the term that we'll be using here. So whenever my lecturer was talking of return, in my mind, just to grasp this, I would visualize it as profit. I would visualize returns as profit. Whenever my lecturer was talking about risk, I would visualize risk as standard deviation. That is the tool from the statistics, standard deviation. But don't worry, we'll cover this when I flip my camera and you can see the paper in which I'll be writing on. So this whole idea is that we want to maximize our investment. We want to get profit from our investment. What will be the use of me investing $100 and then after some long time, let's say after a year, I will get back that $100 without any profit in it? I would prefer to do an investment like, let's say I invest my $100 now, and then after like 12 months, I get something like $150, you know. So we'll also see in this discussion that the higher the returns or the higher the profits that you'll be getting, it is associated with higher risk, you know. Yeah, let us continue. Let us do little talk and do more of the work. But you must note that some of those advanced mathematicians will get bored watching this video, because I won't be doing proofs for this video. I'll be mainly, I think I'll do 2 derivations. Yeah, so it's kind of a beginner's version. It's not for those advanced people in this field. I'm still an intermediate. I'm still a student. Yeah, let us continue. So if you are looking for advanced stuff, I suggest that you go to other videos or go to read other materials online, because this one will try to cover the basics that are needed, which are essential for this Markowitz mean variance analysis. Enough with the talking. Let us get our paper and pen and do some work. Okay, I'm still setting my camera. Okay, yeah. Okay, I think that's much clear. Okay, have to get a clean paper to write on. I've just introduced you guys to what we call returns. So this is our portfolio theory. This is our portfolio theory. In portfolio theory for this video, we'll be focusing on the mean variance analysis. The mean variance analysis. So there's something called short selling. I'd like to start here. Short selling. It is possible to sell an asset that you don't own. If I go, this is me, I go to person A and then I borrow their asset. Let's call their asset X. I borrow their asset and then I sell it to person B. I sell this one. So if let's say this asset is 100 bucks, and then when I I sell it to this person, let's say I sell it with a value, now when I'm buying it back, its value has gone down. This person will buy this asset for 100 bucks, and then when I'm buying this asset, let's say it's something like now 70 bucks. I'm giving that person back. What am I doing? I'm buying for 100 bucks. That's where I'm making profit. Let me see. Does it make sense? I buy for 100 bucks and then I sell it for that 100 bucks. 100 bucks. And then when I'm buying it back, I'm buying it at a value of 70. Yeah, it makes sense. It makes sense. Now the profit that I'll be making, because the value, this means at market, the value of this asset has actually gone down. So my profit will be equals to 100 minus 70 is equals to 30 bucks. I'll be making a profit of 30 bucks. Okay, let me explain what I did here because I nearly confused myself. Let's say today this asset X is costing 100 bucks. I go and borrow this asset from person A. I buy this asset for 100 bucks and then I sell this asset to person B with 100 bucks. At a later stage, this asset's value dropped to 70 bucks and then I decide to buy this asset for 70 bucks. I sell it back to this person for 70 bucks. I'm selling it back to this person for 70 bucks. This means that I'm making a profit of 30 bucks. So that is the whole idea behind the short selling. So short selling is actually selling a pricing that you've borrowed or selling the assets that you don't own. This is the process of short selling. Sorry if I confused you guys, but that's the process of short selling. It's not as complicated as you can think. Okay, short selling, basically selling off an asset that you don't own with an idea of making profits. This whole thing can be risky. What if as I bought this asset X for $100 from this person A, now the value just goes up instead of this value going down. Let's say this value goes up to $150. Now I have to sell to this person back for $150. It's like I'm paying. It's a loss. We want to gain. We don't want to pay. We want to make profit. So this whole idea of short selling can be risky. So some companies have rules that govern this short selling. They don't allow, some of them don't allow this short selling. Some of them have rules. You should go and read about this short selling, but let us not focus more on that one. Let us talk about the returns. We have something called return, and then we have something called the rate of return. I told you, when you are thinking of return, think of it as if it's like profit. So this is return. This is actually the relationship between return and the rate of return. So this is the big return, and this is the rate of return with a small r. Ne? So look here. We've made profit. We've made return. Ne? We've made return. It's like profit. So that's what we'll be doing in this mean variance analysis. We'll be studying how our investments are going to behave. We are not sure of the future, but we want to predict it using these tools, the statistical tools. Let me get straight to a point without wasting any further waste of time. So now we have something called a variable, and then we have something called the expectation of that variable. So we know that from statistics that a variable can be random or a non-random variable. So if a variable is random, let's say x is a random variable, If x is a random variable, this means that the expectation of x must be equals to something like this, the mu of x, because x is a random variable. But if x is known, x is not a random variable, this means that the expectation of x must be x itself. I know this is kind of confusing, but calm down. We'll try to do an analysis of this one. Okay, so this is what I'm talking about. Forget about this one. So for x random, let's say from x you can choose A, B, C. You can choose any value with their associated probabilities of A, probability of B, probability of C. Ne? Remember, I told you that the expectation of this x, since x is random variable, I said it's equals to the mu of x. It's like the mean. What does that mean mathematically? A summation from I is 1 to n of these things that are inside here of x multiplied with their probabilities. So for this instant, the expectation of Ux is equals to A itself multiplied with the probability of A, B multiplied with its probability of B, plus OC multiplied with a probability of C. This is like the mean of x. That's why I told you that the expectation of a random variable is equals to mu of x. But if x is known, let's say we know that x is equals to 2. This means that the expectation of OX must be equals to x, which is equals to 2, because we know that x is 2. For known variables, its expectation must be equals to itself. Now we are doing some work. Okay. Linearity holds for when you are dealing with variables. Let x maps y be variables. Let's just say x and y are random variables. Random variables. Okay, there's less space. Let x and y be random variables, and alpha maps beta be elements of the real numbers. So the expectation of alpha x plus beta y must be the same as, because these are known. Okay, let's start applying the linearity. Let me write this side because I don't want to skip steps. Because there is a plus here, you'll have the expectation of alpha x plus the expectation of beta y. Same thing if you had a minus here, you'll have the expectation of alpha x minus the expectation of beta y. But let's stick to this this case. So our expectation of alpha x plus beta y must be equals to expectation of alpha x plus expectation of beta y. So because alpha and beta are known, they are elements of real numbers, then their expectation is known. Remember that the expectation of a known value must be itself. So this is equals to alpha multiplied by expectation of x plus beta is known, it's equals to beta multiplied by the expectation of y. We stop here. Because x and y are random variables, let's just stop here. Okay, someone might decide, let us go further and write this as alpha mu of x plus beta mu of y. Why? Because this person knows that x and y are random variables. And then we remember, if x and y are random variables, their expectation must be equals to be their mean. That is, x is random. X is random. This implies that the expectation of x must be equals to mu of x, as I did here. Y is random. This implies that the expectation of y must be equals to mu of y, as we were doing here, as I was teaching you here. So basically that is the linearity of these random variables. You must be careful when doing this analysis. Check if x and y is known before you can apply this linearity, because it can cost you marks if you don't guard against these things. Okay, so we are done with the linearity under this Markowitz variance analysis. So thus far we did short selling, we defined what is short selling, and then we did the linearity of these random variables, and then we did what do we call this one, the expectations of these random variables. But let us continue. Now, before we close this video, you will see that later when we're doing our analysis, we'll have some kind of a Cartesian plane like this one, whereby we'll be plotting, we'll be deciding our investment on this graph. This is actually called a mean variance analysis. Mean variance analysis. Why is it called a mean variance analysis? Because you'll be making your decisions on this mean, on this. This is called mu, but you can call it mean. It's a mean variance analysis. The mean is like the profit I told you earlier, and this is the variance. Variance is our statistical tool to measure risk. So this is where we'll be doing trade-off. This is where a smart investor will be looking where they should allocate their wealth in order to achieve greater returns, in order to achieve profit, in order to achieve returns. Yes, I'm right, returns. So we'll be looking at something like this. Okay, let me just do this. So we can see at this, let's call this sigma 1. You can see from here, you can draw that vertical line with your ruler. Sigma 1 on this graph is pointed to mu 1 and mu 2. A smart investor will choose to invest here than this one, because they can see at the same risk they are getting a higher return, they are getting a higher profit. Remember, I said the return are profits. They are getting a higher profit compared to this one. Okay, let's try to be rational. Why would you invest here instead of here? Because you can see you have the same risk, but the return here is much higher than this one. So basically, that's what these investors will be doing. So we will be trying to understand the investment, the choices that these investors will be making using this type of analysis, which is called the mean variance analysis, because they want to make their decisions in order to optimize their profits, in order to optimize their returns. That's the whole aim. And this is related to trading. You can see traders. For traders, what they are doing, it's very risky. But the higher the risk, the more return or the more profit you'll be making. The lower the risk, the lower the return or profit you'll be making. Okay, let us continue. Thus far, it's good. Okay, I need a blank paper to write on. I hope you are still following. If you are still following, you should give yourself a high five, because I'm still excited and have the energy to do some work. Okay, here we're talking about this mean variance analysis. I told you that this variance, it is our statistics tool to measure risk, and then this one is our statistic tools, this mean, to measure return. Let me write on a neat page because there's just too much there. People will be scared seeing, this guy is writing huge things. Can't deny there's no huge things. I'm just doing basics. Okay, look, I told you that this is called it is sigma. This one, ne? It's a standard deviation. We'll be using it to measure risk. And then we have mu, like this one. It's a statistic tools that we'll be using to measure returns, ne? Which you can call profit. So that's what we'll be doing. Okay, we know that at the end of this lecture we should see something very interesting. Why am I saying it's a lecture? Okay, so let's take our random variable x. Let x be random variable. Now we want to find the variance of x. Variance of x. This is the same as the variance of the return on x. So if I start using r of x instead of x, just know that I'm actually doing the same thing. So normally I don't like to write variance of x. I like to write variance of r of x. So the variance of x must be equals to, this is a definition, the expectation of r of x minus mu of x, all squared. So if we split this, it's equals to, remember I'm just multiplying these two brackets, it's like this now, r of x, mu of x, minus. So the student should be happy to see this, because I think the student should pause and try to multiply or spread these two brackets alone. I hope the student did pause and attempted to spread this alone. The student should come up with something like this. So r of x multiplied by with r of x, it's r of x squared, r of x multiplied by mu of x, and that's r of x, that is plus mu of x. I just spread multiplied this to come here. It's still under the expectation, né? So it's your job to actually confirm that we come to this one. Okay, look here, because we are having a subtraction and addition inside our brackets, this means we'll have separate terms of expectation. Okay, the student should note that this is supposed to be a square. This multiplied by this, it's a square. Né? Yeah. Okay, so we'll apply this again. Remember, when we have things that are adding as we did inside our bracket of the expectation, this led to something like this, and then we did I won't be, excuse me, I won't be explaining this again. Let's just to stick to what we have. So it's the expectation of r of x squared minus 2 mu of x r of x plus mu of x r squared. Basically, I'm just writing these expectations r of x squared in this fashion minus expectation of, this, okay, let's just 2 mu of x r of x, this whole thing, and then this one plus the expectation of mu x squared. This is what I'm writing. I think I need another paper here so that we can do we can continue with our arithmetic here. It's not actually arithmetic. So okay, so remember that x is the random variable here, and I told you that instead of writing x, I'll be writing r of x. Variance of x equals to the variance of r of x. So this is random. Let's just leave it as it is. Expectation of rx squared is like expectation of x squared. Since it's random, we don't want to go through that route of saying the expectation of x must be equals to mu of x for now, for this one. 2 is known. We can factor out 2 as we did with alpha was known. Alpha and beta were real numbers. So we actually factored out alpha and beta here on the last example that we did. But since x and y were random, we left them as they are. And then I decided that, okay, because x is random, the expectation of the random variable must be equals to mu of x. Same thing with this random variable y must be equals to mu of y, its expectation. Okay, 2 is known and mu of x is known, so we can factor those out. Minus 2 mu of x. The expectation multiplied with the expectation of our random variable x. Oh, like x. Yeah, I'm right. Plus mu of x is known, so this is like the same as I told you. When x is known, this means expectation of that known value must be equals to itself. So expectation of this mu squared, which we know that what is mu is the same as mu of x squared. Okay, let us continue this now. Expectation of r of x would give us, okay, let's write this as it is, x squared minus 2 mu of x. This would give us mu of x again plus mu of x squared. I told you this is random. Since our x is random, this would give us mu of x. I won't be dwelling that much on this one. This and this one will be adding with one another. So this will be like minus 2 mu x squared. So it's like minus 2 mu x squared plus mu x squared. And then we bring that again r of x squared, and then let me get this very neat paper. I don't want to. Okay, so where were we? I hope you guys are still following. So this is where we are. Forget about this one. So this is nothing but expectation. We just write this as it is. Let me write here because it can lead to confusion. R of x squared. So minus 2 plus a 1, it should give us minus 1. And remember that we said let x be a random variable earlier initially. Let x be a random variable. And then I wanted to calculate the variance of this random variable x. And then I could see that by definition, the variance of x must be equal to the expectation of that random variable x minus mu of x. And then I multiplied through, I applied linearity and so forth. And then now I can come to the conclusion that the variance of r of x must be equal to this. Variance of any random variable must be equal to its expectation squared minus the squared mean, the squared mu. So remember I told you that variance, the standard deviation, because variance is related to standard deviation. I will show you how. Variance is our statistics tool that we'll be using to measure risk. The mu or the mean is actually the statistic tools of measuring risk. I think I wrote this graph here as I showed you. It was a mean plot against the variance. Let us continue. I hope the student is still following. Now I want to show you the relationship between sigma and standard deviation because it could be confusing. Trust me, I got confused a couple of times. Now how can I put this? Remember that variance of x, which is equals to variance of r of x, must be equals to the expectation of r of x all squared minus mu of x. I hope this is showing. Yeah, it's showing. I can see. So this is the definition of variance. Let me put a nice highlighter. The reason why I don't want to use the stick marker, it's got a strong smell. That chemical, it's actually a permanent marker. So this chemical is making me dizzy. Yeah, so I will try to interchange it because I don't want to inhale too much of this permanent marker. Okay, that was the definition of the variance of x, which was equals to that expectation. Oh, sorry, I'm forgetting that squared. The expectation of r of x squared minus mu of x squared. I just derived that one. It's very easy. You can derive it on your own. Remember that definition for variance of x must be equals to expectation of r of x minus mu of x all squared. And then you can spread that brackets, apply linearity to actually get to there. Okay, now I want to show you something. I want to relate to you the standard deviation to variance. Normally you will see when we do that Markowitz problem, at the end we'll be doing something like this, that sigma must be equals to the square root of variance of x. That is sigma. Now this implies that the variance of x must be equals to, so I interchanged, because now here you can see that this sigma of x is equals to the square root of its variance. This means that variance, now if I make variance the subject of the formula, this means that is equals to sigma squared. That's the relationship between variance and standard deviation. So in this statistics approach, we are using we are actually using the standard deviation, this one, as the measure tool of as a measure tool to measure risk. And then we'll be using mu, as I've shown you. The mu is something like this. We'll be using mu as a measure, as a statistical tool measure to measure returns and profits. But let us try to dive in deeper. I know it's kind of boring. Suppose x1 and x2 are random variables. Now we want to find a variance between this x1 and x2. Now when you are finding variance between two variables or between two assets, we no longer call it variance. We call it covariance, because it's now between two. Initially we were dealing with variance because we had one very random variable of x. Now instead of writing variance, I'll write covariance of r of x1. We can call it 1 maps r2, which is equals to covariance of x1 maps x2. Remember, I told you I don't like writing this x's. I'm more interested in writing in this fashion, but it's up to you. Try to stick to what you are comfortable with. So the covariance between these two random variables of x1 and x2, it would be expectation of r1 minus mu1, r2 minus mu2. So remember that when you had one random variable which was x, you had r of x minus mu of x all squared. But now you have expectation of r1 minus mu1. Instead of squaring this, you put the second bracket as r2 minus mu of 2. This is covariance between x1 and x2. This is variance of this matrix, of this random variable x. So if we spread this, we come to something like this. It's really easy. You just multiply through. So it's r1 r2 minus r1 multiplied by mu2, r1 mu2 minus r2 mu1 plus mu1 mu2.